All right, we saw a numeric example of how those derivatives get computed. It's just really simple computations. Now let's go back and interpret a little bit what the derivative means. So let's say we have a particular parameter that we're trying to update, wj, and we have a particular data point xi. We look at its contribution, and it turns out that for xi, hj of xi has value 1. Let's say that that's what happened. So what is the contribution that this data point has on the total derivative? So if you call this contribution here delta I, and I chose hj of xi to be 1 because then we don't have to worry too much about feature value. We can just focus on that difference. Let's interpret that difference. So let's first look at the case where yi is positive. It's a positive training example. And our model is pretty sure that it's a positive training example. So it says the probability that y equals plus 1, it's approximately equal to 1. So let's interpret what happens. So in this case, delta I is going to be equal to the difference between 1, the indicator function is positive, and the probability here, which is approximately 1. So this whole thing is going to be approximately 0. In other words, the data point is positive. The model thinks it's a positive data point. So the contribution here is 0, means don't change anything. From the perspective of this parameter, you shouldn't change anything, which makes sense. You get it right. But let's see what happens if you're getting completely wrong. So this is the second case where it's a positive training example, but the probability that y equals plus 1 is approximately 0. We're getting this training example totally wrong. In this case, delta I is the difference between the indicator, which has value 1, and the probability here, predicted probability, has value 0, and so it's approximately 1. So delta I is really big. And so what does this imply? This implies that this data point wants us to increase the coefficient wj, the one that we're just trying to increase. It says push the derivative up, add this little delta that makes it more positive. And remember that if hj is a positive number and it's multiplied by a bigger coefficient because we just made it a little bigger, that implies that the score of hi becomes larger, and that implies, in a sense, the probability that y is equal to plus 1 given xi and w increases. But that is extremely intuitive. So if we're getting the data point really wrong, we get this positive delta I, which is going to increase my parameter, which is going to increase my score, which makes in the next step, the next iteration, the probability that this data point is positive higher. So we're going in the right direction. Now, just going to go through this a little quicker. We can look at the case where yi is negative, and you just get the same thing with flip signs. So for example, if yi is negative, but I'm getting the prediction right, so this is a negative data point, we'll see that delta I is approximately equal to 0, which implies, don't change anything. It makes sense. I got everything right. Why would I change anything? However, in the case where the data point were negative, but the prediction I made was it were a positive data point, then delta I would be the difference between the indicator, which in this case is 0, and the probability, which is approximately 1. So this delta I would be negative, would be approximately minus 1, which would lead wj to decrease, which would imply that the score of xi decreases, and it leads to the probability of y equals plus 1 given xi and w to decrease. Yay! If it's a negative data point and we get it wrong, we decrease the coefficient to make that probability of it being positive smaller and increase the probability of it being negative. So cool. We've gone through a little bit of interpretation of how this gradient helps us push either the coefficients bigger for positive training examples and more negative, smaller for negative training examples, which is exactly what we wanted for that score function.